go. Hello, everyone. Okay, intermolecular forces. Okay, so what was I saying? That changed. Perfect. How is everyone tonight? Just got home a little bit ago, so I'm just finishing getting everything set up for our review session today. That's what I need. This is going here. What's up, everyone? How is everyone's... Is today Monday? Yes, I looked at my calendar. Today is Monday. How's it going? Today, we are going to be going over intermolecular forces and gas laws. So give it about 5 minutes if you want to follow along. Most of the problems are online. I added some later on, but they are on my link tree. If you just click the link in my bio, it'll take you to a Google Drive, and you can get a packet of everything that we're going to be doing today. The questions-wise, we'll go over everything for about 5 or 10 minutes. Hello, how are you? I'm doing great. I had a really good day today. And I got sushi for dinner, which was amazing. I love me some sushi. So I had sushi and sashimi and crab rangoon and fried ice cream. It was a lot. I splurged a little bit for my dinner. But I hope you are all doing fantastic. Let me finish setting this stuff up. There we go. Perfect. All right. So I think everything for the most part is set up. So we'll give it just a couple minutes and then we'll hop right into some review on intermolecular forces and gas laws. Is anyone taking the AP Chem test and starting to get a little worried? Hello. A little stressy and maybe some stressy and depressy. Because I think it's, 3 weeks away? 3.5 weeks? The AP test? It's under a month, I know that. How many days until May 6th? It is 3 weeks away is the AP test. Not to scare anyone. This is the point where I would go online and take a diagnostic test to see where you are in terms of the material. A diagnostic test is not to be reflective of what you are going to score. Like, don't think you're going to know everything when you do a diagnostic test. It's just a matter of where you are at the current point in time and what you need to focus on. And there's a bunch of different online resources, or they have the ones in the review books as well. You have quantum mechanics on Friday, and it's eating me up. Quantum mechanics, that's a tough one. So are we talking quantum as in like general chemistry quantum, or a specific quantum mechanics class? Both are difficult, but one is just like a whole nother level. It's like the Gen Chem one, boom. I got a 4 on the most recent diagnostic. I feel like getting a 5 is impossible. It is not impossible. It is not impossible. A 4 is really good on the most recent diagnostic. You have 3 weeks to brush up on the topics that you aren't really great at yet, that you haven't really mastered, and that's totally okay. That's totally normal. You're actually one step ahead of the game, because I start giving diagnostic tests to my students this week for them to get ready. P-Chem 2 quantum mechanics, yeah, that's definitely a tough course. Practice AP test, I'm in class. How long are you going to be live for? Oh, we'll go back to class. I will be live probably for an hour and a half, but all of these lives are posted on my YouTube. I haven't started studying. I'm stressed. What should I do? Well, first, take a moment. Take a breath. Don't be super stressed. What I would do is map out a plan. Go over your notes. Just sort of look through your notes, the general gist. Don't go in depth with those, and just look at them and say, this is what I know, this is what I don't know. This is where I could brush up a little bit on. This is meh. And then from there, you sort of create a study guide of units, and then you can sort of go a little bit further there. College is hard. There's a lot of different courses. Can you help with Vesper? I did Vesper 2 days ago. So that video is on YouTube, and all of the practice problems and answers are on the Google Drive that I have. So if you need help on Vesper theory, definitely go check out that video. It's the latest one, Unit 2, I think. Let's see. Can you what's your dissertation on? That's a whole thing. In a nutshell, I work with nanoparticles and their interactions with the body and biological things, so very, very tiny glass beads, to look at the interaction with biological systems for drug delivery and everything. So I don't want to get into a lot of it now, because we are going to be doing some Gen Chem review and AP Chem review. Have I done acid-base? No, that is on the list for next week, I believe. Stoichiometry is Saturday, so that's going to be Saturday. Hardest chem class? Ooh, physical chemistry right now, I think, would be the hardest. Okay, so what we're going to do... Yes, Stoic. I'm so happy everyone's so excited for Stoic. Stoic is going to be Saturday's review session, I believe. Maybe earlier if I can get around to making the material. So before we get started, if you do want a copy of the practice problems, they are on my link tree. So if you just click the link in the bio and follow the steps to get to the Google Drive, you should have access to this. There were some issues. Do you have a video on how to know if it's dispersion forces, dipole, etc.? No, but guess what? That is exactly what we're doing today. We are going to be working on intermolecular forces, so I will have a video soon, because we're going to do it. So let me finish getting all of this stuff set up. I am going to... You'll see my ceiling for a moment. I was using your video on protein synthesis for... Oh my goodness. There's so many people trying to request, and I love requesting people, but I was using your video on protein synthesis for an AP Bio project. Oh, thank you. I feel like maybe you were the one who reached out to me and asked if it was okay. But if not, that's totally okay. Anyone can use any of my videos, because I'm a creator. I create to educate. So there's that. You're going to see my ceiling for just a moment while I get the camera set up. We turn that and we flip camera. There we go. Oops. Come on. There. All right. And I also fixed the whole, what was I going to say? I fixed the whole auto brightness thing, so that shouldn't be a problem tonight. But what we're going to go through are some notes. So as always, these review sessions, the first 10 to 20 minutes, are going to be sort of a general guide. So some notes, like a lecture style review, and then we'll jump into those practice problems. So today we're going to be talking about intermolecular forces, as well as gas laws and some solids, like properties of solids and stuff like that. But primarily it'll be focusing on our intermolecular forces and our gas laws. I'm just going to make sure that it's not doing the whole zoom in and out. It is going to, but that's okay. We'll work with it. So when we're talking about intermolecular forces, that is a big term. You may see this as denoted as IMF. So if you see something IMF, that's just intermolecular forces. Those are forces between molecules. So last time when we were talking, we were talking about bonds, so like an ionic bond, a covalent bond, or a metallic bond. those are intramolecular. They are within one molecule. But here now we're talking about intermolecular forces. So these are forces between molecules. And so a good way to think about it is just the root phrase inter versus intra, right? So inter, if you go travel internationally, you're going from one country to another. So you're using more than one country. Here, we're talking about intermolecular. So international, more than one nation. Intermolecular, more than one molecule. And so when we talk about intermolecular forces, these are going to be forces between more than one molecule. And we have three main types of intermolecular forces. Now, there is going to be a sort of a fourth one, but we'll get into that in just a moment. The first type is called London dispersion forces, or LDFs. So London dispersion forces, or LDFs. These, I'm going to keep with blue, I think. Everything has LDFs. So no matter what molecule you are talking about, whether it's polar, nonpolar, whether it's covalent, anything like that, it's going to have London dispersion forces. So no matter what molecule, if we have Cl2, CH3Cl, if we have HBr, we have a very big molecule, we have a very small molecule, everything is going to have London dispersion forces. Now, these are the forces that we call, that come from a temporary dipole moment. Now, a dipole moment, remember, that is just our difference in electronegativity. So when we're talking about bonds, when we're talking about like a carbon-chlorine bond, we looked at the electronegativity of carbon, we looked at the electronegativity of chlorine, and we saw that chlorine is more electronegative, giving us a partial negative and a partial positive. So partial negative on the chlorine, partial positive on the carbon. And we created a dipole moment where now we have a sort of negative charge favoring one direction versus the other. A negative charge is closer to that chlorine. And so when we're talking about a dipole moment in a bond, that's what we're talking about. But when we talk about a dipole moment in a molecule, that's going to be the overall net dipole moment. So something like, we'll start out with something fairly simplistic, which is H2. So a bond between H and H. So H2, molecular hydrogen. This bond here, we look at the electronegativity between hydrogens, and they are the same. So we don't have a complete permanent dipole moment, right? There's no change in electronegativity. This is 2.1 and 2.1, I believe. So the overall net dipole here is 0. So we don't have a dipole moment. However, electrons, so we have 2 electrons here in this bond, and they're being shared equally between those 2 hydrogens. But those electrons are moving around in space. They're moving around that molecule. And when you're moving around in that molecule, at some point, you might have those electrons closer to one of your hydrogens just for a split nanosecond. But those electrons are going to be closer to that hydrogen. And that's going to create a very partial negative, very quick and very partial negative charge on that hydrogen and a partial positive on that other hydrogen. And so this sort of temporary dipole lasts for a moment and then it goes back to being happy again. So our electrons here are going to be shared between those. So it's really just using your electronegativities exactly. And we'll talk about sort of a cheat to this to sort of look at our intermolecular forces. But that doesn't really help us with this intermolecular, right? We're talking about in a bond, in a molecule, we have a partial positive and a partial negative. But what we're really talking about is, I'm going to get rid of just some of this stuff. I'm going to start over with the H's here. So if we have this H2 molecule, and those electrons are closer to that hydrogen, giving us that negative charge on that hydrogen and a positive on the one on the left, then what we see is if another H2, another molecule of H2 comes into play, comes near this other H2 molecule, and it also ends up becoming partially negative on one side and partially positive on the other side. Well, now opposites attract. So now we're creating this force here where the negative side of this one molecule is interacting or wants to attract the positive side on another molecule. And this is the IMF that we're talking about. It is the intermolecular force. It is the force that holds molecules together, more than one molecule together, right? So we have covalent bonds or some type of bonding, and then we have intermolecular forces between two or more molecules. And so this temporary dipole moment where our electrons are favoring one atom over the other, that's going to create a negative and a positive area on our molecules, creating that dipole moment where we have the positive and negative. And if two or more molecules experience that and they're in close proximity, they can be attracted to one another. Inter versus intra, exactly. Intra is the bonds themselves. Inter is the force between those molecules. Now, everything has LDFs. Everything has LDFs because it's temporary dipole moments. So if you have something that's nonpolar and something that's polar, you are going to have LDF, or London dispersion forces. However, the way I like to think about it is they are going to be the most prominent in something nonpolar, because everything polar is going to experience a stronger intermolecular force. So I like to think of London dispersion forces, yes, as everything has LDFs, but they are the most prominent in things that are nonpolar, or things that do not have a permanent dipole moment. All right. If you have any questions in the chat, just feel free to drop them in. I am going to go yes, thank you. I do have that written down, but I forgot. They are also known as van der Waals forces. So if you see the term van der Waal or London dispersion, LDFs, then you are going to, they're talking about the same thing. Because polar bonds are nonmetals and metals. Polar is not nonmetal and metal. That would be an ionic bond. An ionic bond, so like let's say an ionic bond, that's going to be between a metal and a nonmetal, and we'll talk about that type of force in a moment. And then polar just means an unequal pole in your electronegativity. So something like, let me see here, something like carbon, CH4. Ooh, it's doing the whole bounce out and in and out thing. Let me just raise that up a bit. Maybe that'll be better. So something that has an equal pole in all directions, that's going to be nonpolar. But as soon as we get something that's not equal, think of it as tug of war. So something that's not equal pole in all directions of your electrons. So each of these bonds in carbon here, carbon-hydrogen bonds, are pulling equally. Those electronegativities create a net zero dipole moment. Versus down here, our electronegativities of our carbon double-bonded oxygen is stronger, creating a dipole moment. So this would be a polar molecule. But we'll get into that in just a moment. So even if it's asymmetrical, it can still be non-polar. I think there always has to be some type of symmetry. So carbon-hydrogen bonds are considered nonpolar, yes. So carbon-hydrogen bonds are considered nonpolar. The bond themselves are considered nonpolar. But the overall molecule, you have to look at the distribution of bonds. We'll get into these examples in just a moment. We're going to go back here. So I like to think of these as nonpolar. Now, dipole forces, these are going to be your permanent dipole. Permanent dipole moments. So unlike this temporary dipole moment where we had to look and see at one split moment, at one split second here, nanosecond really, those electrons are focusing more on or leaning more towards one atom. This is a permanent dipole moment, meaning this is going to be everything polar. So everything polar, that just means we have a permanent displacement of our electronegativity. Something like, I'm not going to use carbon because we use that a little bit, but something like we have NH3, something like ammonia, where we have sort of an equal pole left and right, but then an unequal pole up and down. And so when we're looking to see if something's polar or not, we look at electronegativities. So we see, think of it like tug of war. If we were to put the center of a tug of war in the center atom right there, and we had our two hydrogens right and left kind of pulling on that nitrogen, that nitrogen is not going to move left or right because you are going to be pulling the same amount. It's like two people pulling 10 pounds right and left. But up and down, we have a hydrogen pulling, but then we have a lone pair of electrons pulling up. And so because our lone pair of electrons is pulling up, we have this dipole moment kind of going upwards, where our arrow tip points in the direction of our electron flow, or where our electrons like to sort of hover. Now, the positive down here, this little dash, just shows us that the positive sign, the positive thing. So this creates a negative and a positive. And this is going to be a permanent dipole because those electrons in that lone pair are always going to be there. And then we have our electrons here, whereas our electrons in our single bond here with our H2, they're just moving around, but they will always sort of be wishy-washy. So we have a permanent dipole moment. So this is everything polar. Now, these forces are a lot stronger. So is that how you determine if a molecule is polar or not? Exactly. Dipoles definitely can cancel out. Yes. So if all we're really looking for to determine if something is polar or nonpolar is, do we have an unequal distribution? I'm going to go back to this example. We have carbon, or methane here, CH4. CH4, we have an equal pull in two directions, left and right. We have an equal pull up and down in terms of our hydrogens pulling on our carbon. We see some symmetry there. But as soon as I change one of those hydrogens to a chlorine, then you start to see a difference. Then you see we have an equal pull up and down, but then an unequal pull left and right. Our chlorine is more electronegative than hydrogen, meaning it's going to pull those electrons closer to it, meaning that we're going to have more of a negative charge on this side always of this molecule, and a positive charge or positive sign over here on this side of the molecule. I saw someone say, always consider the geometry of molecules. Absolutely. Geometry and Vesper theory definitely comes in handy because you may see something that looks nonpolar, but as soon as you put it into your Vesper theory, into your geometries, then it really is either nonpolar or polar, whichever the opposite was that I actually said, because I forgot. But this is a nice way just to sort of see the difference between something that's nonpolar, complete symmetry, versus polar. We have an unequal distribution of electrons. And so these two forces, we have London dispersion and we have dipole-dipole. Those are the two. And then we have one more, and that is hydrogen bonding. Now, hydrogen bonding is a type of dipole-dipole force. It's just a stronger version of dipole-dipole. So this will always have a permanent dipole moment, but it will always, always, always have a hydrogen bound to a nitrogen, a hydrogen bound to an oxygen, or a hydrogen bound to a fluorine. It will always have a hydrogen bound to NOF or NOF. It has to be directly bound. If we had something like carbon with two hydrogens here and that was double bound to an oxygen, well, in our molecule, we have a hydrogen and an oxygen, but we don't have a hydrogen bound directly to that oxygen. There's a carbon in between. And so we have to remember that with hydrogen bonding, we have to have a hydrogen bound directly to NOF. Oh my goodness, I have never heard that. Hydrogen likes to have fun, or FON, F-O-N. I am actually going to use that, if you don't mind, because that is absolutely incredible. I've always just gone NOF, but hydrogen likes to have fun, FON. I really, really like that. So these are our three types. These are our three types of intermolecular forces. Three main types, I'll say. There are different variations of these. You could have a dispersion dipole. You could have a dipole, a temporary dipole versus whatever it is. There's a bunch of them. But these are the three main types that we have. Now, I wrote these in this order for a particular reason. And that's because we have the strength of these. As we increase our intermolecular forces, as we go from our London dispersion to dipole-dipole to hydrogen bonding, those are our strengths. They become stronger. So the forces between these molecules become stronger. So London dispersion forces, those are the weakest force. So London dispersion, even though everything has it, those are the weakest forces. The next step up is dipole-dipole forces. Those are stronger forces. And then on top here, we have hydrogen bonding. So hydrogen bonding is the top intermolecular force, the strongest intermolecular force. Not stronger LDF, stronger IMF. I hope someone caught that. I caught it before I saw it. So stronger IMFs, intermolecular forces. So as we increase London dispersion, dipole-dipole, hydrogen bonding, we're increasing our strength in our intermolecular force. But why does that matter? Well, let's think about it. If we have a stronger intermolecular force, if we have a force between a molecule, so AA and let's say BB, the force that exists between this molecule here, if this force is very, very strong, it's going to have a higher boiling point. Exactly. It's going to have a higher boiling point. The molecules are going to be sort of sticking together longer, so it's going to take more energy for them to break apart and go from the liquid phase to the gas phase. Boiling point increases with bonding strength. Yes, so our intermolecular force strength increases, our bonding or our boiling point is going to increase as well. So there's a lot that we can tell based off of intermolecular forces based on the molecules. So they have higher everything, viscosity, melting point, exactly. If we think about if you've ever had water in a cup, and you pour water into a cup and you start pouring it, and I'm going to do it this way, and it starts to go over the edge, and up and above the cup, that's our surface tension, and that all comes from intermolecular forces, those forces in water. So if I were to draw water out, we have H, O, and H. Well, that is a lot of valence electrons around there. Let me just do a lone pair and a lone pair. We have hydrogen bonding, right? We have a hydrogen bound directly to our oxygen, and that is our hydrogen bonding. So we have a very strong intermolecular force that allows the water to kind of stick together up and above the lip. And that comes with viscosity. If we think of honey or molasses, it's very slow moving because all of those particles, all of those molecules are stuck together. So this tells us a lot of different things. I'm going to answer a couple questions here before I go on. Is it true that branching of a molecule also increases boiling point? I believe branching decreases boiling point. So if we are looking at a linear versus a branched, let me look at this. I'm just going to double check before I actually talk about it. So many things. Branching. Yes. So, there's a lot of messages now. Yes. So surface area. So if I were to look at this molecule here, and we're just going to imagine there's a lot of hydrogens around here that I'm not drawing in, versus something like this. We have more surface area here for all of those temporary dipoles to happen. So we have a lot more surface area for like a positive charge and a negative charge and a positive and negative, whatever it may be, versus here we have less surface area. It's all condensed. And this just allows us a little bit of room. So as we start to have a more linear molecule, we're going to have higher surface area and higher LDFs. Versus branching, we start to get very little surface area. All right, so we have branching for one. There are a couple others, but we're going to go through, let's see. We're going to go through and figure out what intermolecular forces are present in these molecules, just as a quick example. So the topic here is intermolecular forces and gas laws we'll get into in just a moment. Dipole, and hydrogen bonding both also have LDFs by default. Yes, thank you for noting that. So let's say we have a molecule that has a dipole. I'm going to use purple here. So we have a molecule that has dipole forces. Because it has dipole forces, it has dipole forces and everything that comes before it. So LDFs are intermolecular forces. If it has dipole, it also has LDF, but our dipole forces are stronger. So they're the more prevalent one. Versus LDF, they're weak, they're in everything, but our dipole are going to be more prominent. Same with something like something that has hydrogen bonding, for instance, that has dipole and London dispersion, but we only look at the strength of it with hydrogen bonding. Okay, so let's figure out what intermolecular forces these have. Starting with 1, we see carbon with 4 hydrogens around it. Now I drew this in our molecular geometry, our electron geometries for carbon. We have carbon with 4 hydrogens. It is tetrahedral. Just as a little review of Vesper theory. 4 things around a center atom gives us a tetrahedral shape. Now, if we look at this, if we were playing 4-way tug of war, we put our flag or the center of the ropes on that carbon. Well, a carbon to hydrogen bond has a certain polarity, it has a certain dipole moment, a difference in our electronegativity, but we have 4 of them, and 4 of them being pulled in equal and opposite directions. So they're all spaced out, they are pulling essentially a 4-way tug of war equally throughout this whole thing. So our molecule here is going to be nonpolar. We do not have a permanent displacement of our electrons. And so because our molecule here is nonpolar, if we go back to our London dispersion, dipole-dipole, or hydrogen bonding, we're just going to work through the list. London dispersion forces, everything has LDFs. So we know right off the bat that this is going to have LDF. Everything has LDFs. Does it have dipole-dipole forces? Well, dipole-dipole forces are only when we have permanent dipole moments or when something is polar. Since we have a nonpolar molecule, this molecule here does not have dipole-dipole forces. And since it does not have dipole-dipole forces, we can stop and we don't have to go on to our hydrogen bonding. Because once we hit a no-go for one, we can stop. So this only has LDF. Now, if we take a look at number 2, well, let's see. Number 2, well, everything has LDF, so we're going to write LDF as one of our intermolecular forces. If we were to look at this carbon molecule here, well, if we have an equal pull up and down on our carbon in terms of electronegativity. So we have a certain dipole moment going up like this, a certain dipole moment going down like this in terms of a pull for electrons. But since those are equal and opposite, those cancel out. So we can get rid of all of those. And then we have a certain pull here, but then we have a different pull, right? We have a different electronegativity. Now, because chlorine and oxygen are different, they have different electronegativity. So one of these is going to be pulling one direction more than the other. We don't know. We could look at the periodic table. We don't necessarily need to right now. But one of these is going to become different. So we're going to have an overall dipole moment in one way or the next. So this is going to be a permanent dipole moment or something that is polar. So something that's polar, remember, if we go back to our intermolecular forces, we have London dispersion, everything has that. Then we have dipole-dipole forces, that is polar. So now we have dipole-dipole as another force that we have in this molecule. And then on top of that, we look to see if we have hydrogen bonding. Now remember, hydrogen bonding is a hydrogen bound directly to a nitrogen, oxygen, or fluorine. Now, because we have a hydrogen here that is directly bound to an oxygen, that signifies to us that we do in fact have hydrogen bonding present in this molecule as an intermolecular force. HNOF, yes, or as someone said, H's like to have fun, F-O-N. How can you tell if it is polar or nonpolar without subtracting the electronegativity? A lot of it comes from practice and just sort of visualizing and seeing, do we have an equal pull in all directions? If we have some type of symmetry where we have an equal pull of electrons in our molecule on our center atom or on our molecule overall, then we're going to be nonpolar if we have an equal pull. But if we don't have an equal pull in terms of chlorine and oxygen are different, then we just say, okay, well, because these two are different, we're going to have a polar molecule. So it's just a lot of practice in determining if something's polar and nonpolar. To start out, you're going to want to look at the electronegativities. And once you do a lot of them, then it'll start to click in your head as to, oh, this is polar because even though up and down is pulling nice and even, left and right, one of them is different than the other. So this molecule here, number 2, has all 3 of these intermolecular forces. Does this tip always work? For the most part. Once you get into expanded octets, it gets a little different, but for the most part, that would work. Now, if we look at this molecule, even though it has LDFs, dipole-dipole, and hydrogen bonding, the strongest one out of all of those is our hydrogen bonding, which means this is going to be the one that determines a lot of the properties in terms of boiling point and such. LDF is London dispersion forces. Those are intermolecular forces. You may have seen them as van der Waals. Those are the same thing. Electronegativity increases while you move right to the periodic table. Yes. So as you go to the right and as you go up, electronegativity increases. Oops. I'll go up. So fluorine is the most electronegative molecule. Yes, fluorine is the highest. All right, let's do number 3. Number 3. We have here, I'm going to go back to red. We have here a molecule. Now, a molecule means that we have LDF, always. Everything has LDF. Now, we need to determine if this molecule is polar or nonpolar. Now, if we look at this molecule, we have a certain electronegativity between carbon and hydrogen, another between carbon and hydrogen, and then we have one with carbon and oxygen, or a double bond between carbon and oxygen. If we think about it like a 3-way tug of war now, we have one hydrogen pulling one direction, kind of like a peace sign, right? So equally spread out, another hydrogen pulling another, but oxygen is much more electronegative than hydrogen, meaning it's going to win that tug of war. So we're going to have an overall permanent dipole moment here. I'm going to erase that so we can see. We'll have an overall dipole moment where our electronegativity is favoring that oxygen. It's going to be closing in on that oxygen, creating a partial negative charge up top and a partial positive charge on the bottom. And since that is a permanent dipole moment, we have a polar molecule. And as we looked at before, everything that is polar is going to have dipole-dipole forces. So we also have dipole-dipole forces here. So we have LDF, then we have dipole-dipole. Now we need to figure out if we have hydrogen bonding. So remember, hydrogen bonding, well, I'm going to keep that. Hydrogen bonding is between, oh my goodness. Hydrogen bonding is between hydrogen and nitrogen, hydrogen and oxygen, or hydrogen and fluorine. So we have hydrogens here, and we have an oxygen, but this does not have hydrogen bonding because those hydrogens are not directly bound to an oxygen. So as we see here, this hydrogen has a carbon in between itself and that oxygen. So it's not directly bound, meaning that we do not have hydrogen bonding. So these are the only 2 intermolecular forces that this molecule has. And so it does not have hydrogen bonding, but it has LDFs and dipole-dipole. And our most prominent, or the strongest one that's going to determine a lot of the factors like boiling point and viscosity and everything, is dipole-dipole. And so this is how we can determine our polarity and our intermolecular forces. What's the easiest way to tell? If we have an overall, a different pull. So essentially, do we have different things? I don't want to use the word pull again. Do we have a difference in electronegativity? If we look up and down, carbon, chlorine, carbon, chlorine, those are going to, I'm going to use pull again. Those are going to pull on the carbons the same in terms of the electronegativities. We have a carbon chlorine here and a carbon oxygen. Since those are different, now it's not symmetrical. And then we can go through and just say that that's polar. Hi, Kayla. I see you here. I saw a question here. What does that sort of S and negative and S and positive mean? Those are partial. So this sign here, this little S, is a partial positive charge, meaning that it's not a full positive. We don't have an ionic bond like sodium where it gets rid of that electron fully. And our chlorine, for instance, that will take an electron and create a full positive and full negative charge. It's just a partial negative where our electrons are sort of favoring our oxygen. And since electrons are negative, they're going to create a partial negative charge. It's not a full negative or a full positive, but it's a partial negative. Sodium takes the electron. It does not take the electron. Is this the same thing as formal charge? Formal charge is a little different. My professor is teaching us that everything is polar except CS, CH, and SH. Yes, polar bonds. I'll say that. Can you do SiCl3Br? I can try. Let's create another page here. Nope, did not mean to clear page. Y'all are gonna see my technology skills. I'm good. Don't worry. There we go. Okay. SiClBr. So we have SiCl3, Cl3Br. So SiCl3Br. If we were to look up or figure out the electronegativity of this, or not the electronegativity, the Lewis dot structure, we would look and say, well, silicon has 4. It's under carbon. It has 4. I'm doing this without a periodic table. So silicon has 4, chlorine has 7 times 3 valence electrons, bromine has 7, so this has a total of 32. Silicon goes in the center, then we put our atoms around it. Then we go through this. Let's see. So then we have a total of 32 valence electrons. So far, we have used 2, 4, 6, 8 valence electrons, giving us a total of 24 valence electrons that we need to put in. And then we can go around starting outer first. We put those in. 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, giving us no more valence electrons left. How do we know the center atom? We look at the least electronegative. So if you look on a periodic table, carbon or chlorine and bromine are in group 7. Those are your halogens. And so they are further to the right on the periodic table, meaning they are more positive or more electronegative, than silicon. So that's going to be in the center. Now what we take a look at let's figure out our intermolecular forces here. So for our intermolecular forces of SiCl3Br, well, everything has LDFs, right? So we can right off the bat say that. Everything has LDFs. So does it have dipole-dipole forces? Well, if we look at this molecule, we are looking for an unequal distribution of electronegativity or an unequal pull on that center atom. So if we were using a tug of war, and I like using tug of war because it's I think a lot of people will get it, but if we put the center of our tug of war right on that silicon, and then we look at the difference in electronegativities, well, chlorine and chlorine, those are both the same electronegativity. So those mean because we have a pull here and a pull here, chlorine has the same, this dot is not going to move up or down in terms of our electronegativity. And then, so we can sort of cancel those out. But our chlorine here and our bromine, I need a periodic table. So our bromine and chlorine are right here on the periodic table. Now, chlorine is up further up. It's closer to fluorine than bromine. So chlorine is going to have is going to be more electronegative. So yes, chlorine, all three chlorines would have the same pull. So I'm going to draw that in. We have the same pull in all directions. And then bromine is a little bit smaller. I'm going to dramatize it for effect. But we have the same pull in all directions for our chlorines, but then the bromine is just pulling slightly this way. So overall, our molecule is not going to move up or down, but if we were to cancel this out, our chlorine pulling this way is going to win in that in that tug of war. So our overall dipole moment is going to be in this direction, where our partial negative charge is going to be closer to this side, and our partial positive is going to be closer to that side. Now, this is all to figure out if we have a polar or a non-polar molecule. So this tells us, because we have these partial positives and negatives, this tells us that we have a polar molecule. We don't have an equal pull in all directions. So because we have a polar molecule, we have dipole-dipole forces. That is characteristic of dipole-dipole. It is a permanent dipole moment. And then, do we have hydrogen bonding? Well, remember, hydrogen bonding is a hydrogen bound to a nitrogen, oxygen, or fluorine directly. Well, there we go. Do we have any hydrogens in this molecule? No. So we do not have hydrogen bonding. So the only two forces that we see here in this molecule are LDF and dipole-dipole. And that would be SiCl3Br. How is a tetrahedral polar? So tetrahedral, remember, let me actually grab a model kit, because I have one. Okay, so let's do some modeling. Oh, look, I even have hydrogens already on. Oh, amazing. Okay, and I'm going to get a carbon. So, if we have something that's tetrahedral, like, oops, this. So let's say this is SiCl3Br, right? So, oh yes, you didn't see the bromine? That's okay. So we have a carbon here. Now this is our tetrahedral molecule. Now if we look, if I kind of put it the same way that we have here, where there are silicon in the center, and then our chlorines 1, 2, and 3, those are the white little balls on the ends, and then our bromine is the green. Well, because we have these three chlorines pulling equally this direction versus the bromine in this direction, now we have a dipole moment where our electronegativity is favoring the left-hand side of the molecule versus our right side of the molecule is just our bromine. So this model kits, if you are able to get one, they are definitely very helpful in visualizing things in 3 dimensions. There are some online websites that you can also use, but getting a model kit, and it's like playing with Legos. It's so much fun. It's so fun. Okay. So LDFs, dipole-dipole, and hydrogen bonding are the 3. So let's see. So if it was 1Br and 1Cl, where would it be favoring? Well, it depends on what else it was. So, if it was, well, it would favor the one with the most electronegativity. So that would be chlorine. So it would favor our chlorine. So it would go towards the chlorine. If you had like hydrogens on here, that's what I would say. Okay, so this live is technically supposed to be about intermolecular forces and gas laws. Do we want to stick with intermolecular forces, or do we want to move on to gas laws? I'm going to see this. He's teaching us FOCLNBRISC. Oh my goodness, wait. What is going on? He's teaching us FOCLNBRI scantium, more electronegative as you go left. Whoa, more electronegative as you go left. No. Okay, so I'm seeing a lot of gas laws and a lot of LDFs or IMFs. I keep saying LDF. I'm so sorry about that. So what we're going to do is we're going to go to gas laws. We'll talk about gas laws, what they are, the different types, and then we'll go into practice problems, which will have practice problems on intermolecular forces and gas laws. So that'll sort of be a contingent thing. But on a normal periodic table, electronegativity increases as you go to the right. So as you start from the bottom left and go up to fluorine, it's going to be you're increasing your electronegativity. So bottom left to top right. Okay, so let's go through some gas laws. So gas laws, always talking about, are we able to have access to these notes? The practice problems that I go over, those I post, as well as the answer keys. I can figure out how to get the notes. They're going to be a little messy, but the YouTube videos are posted, or this live is posted on YouTube. So, they're messy, but sure, if you want access to my notes, I can definitely do that. I can try to clean them up a little bit too. Okay, so gas laws. We have a lot of different things when we're talking about gas laws. We're going to be talking about pressures. So pressure, we're going to be talking about volumes. We're going to be talking about temperatures and some other variables, okay? So when we're talking about gas laws, there are a bunch of variations that we're going to look at. But what really comes into importance is what comes after this page. So we'll talk about these briefly, and then we'll talk about what's coming up after that. So when we're talking about gases, we are looking at the pressure of gases. We can measure the volume of a gas. We can measure the temperature of a gas. We can also measure our number of moles of a gas. We can collect our gas over water, or we can just do some measurements. And all of those people have found have been related to one another, where if you increase pressure, something happens to your volume, or if you decrease temperature, something happens to your pressure. So there's a bunch of different things that we can look at to figure some of our relationships out. So some guy named Boyle, whoever Boyle was, came up with a law that he named after himself, or someone named after him. And he ran a lot of tests, and he found that the pressure of a gas is proportional to its volume. So it's proportional in the sense that, well, as one increases, the other decreases, the inverse. So let me rewrite this in terms of Boyle's law. Well, we can say, according to Boyle's law, that pressure of some system, so P1, V1, P1 pressure times volume, equals our new pressure times our new volume. So let's say we change the pressure from 5 to 7, then our volume is going to change. It's inversely proportional. Yes, sorry. So this is saying, well, as our pressure increases, our volume has to decrease. So as one increases, so as pressure increases, I'll do this, pressure increases, our volume must decrease, and that is inversely proportional. So Boyle's law found that pressure and volume are inversely proportional, meaning as one goes up, the other goes down, and vice versa. Then Charles came along. No idea who Charles is, but Charles came along. And Charles found, after doing a bunch of things, that volume and temperature were related. That as we increase or decrease our volume, our temperature also increases or decreases proportionally. They are directly proportional. As one increases, so as volume, I'm going to use green again, as volume increases, so does our temperature. So we have this relationship, V1 over T1 equals V2 over T2. Yes, this is definitely very important. Anytime that we are working with temperature, we have to be in Kelvin. And the reason for that is if we are talking about temperature in, let's say, Celsius, well, we can have something that is 0 degrees Celsius. There is an actual value, 0 degrees Celsius. But we can never divide by, so if we had a volume here, divided by 0 degrees Celsius, in math, we cannot divide by 0. And that tells us that, well, since we can't divide by 0, we have to be in a unit that gives us something, a temperature that is not equal to 0. And so we cannot be in Celsius. Anytime we're working with gas laws, we are going to want to be working in Kelvin. So when we're going to go from Celsius to Kelvin, for instance, yes, we are going to add 273. So I'll do this here. Temperature equals degrees Celsius plus 273. So temperature in Kelvin, you take your degrees Celsius and you add 273. Now, Avogadro also comes in, and Avogadro, we know as Avogadro's number, so we're talking about moles, and there's a relationship between moles and temperature. I am forgetting this because I didn't prep beforehand. And now all of my notes are out of order. No one really cares about Avogadro's law, if I'm being completely honest. I've never seen it asked before. It's proportional between volume and n. Yes, okay. So Avogadro's law states that our volume is proportional to our number of moles, meaning that our V1 over N1 gives us V2 over N2. So V1 over N1 equals V2 over N2. Now this is, we have to have some constant here though. So that's times some constant. So we have V1 over some constant N1, V2 over some constant N2. We sort of forget that constant. But Avogadro's law says that we have a relationship between volume and number of moles. And in fact, I saw it in the chat a little bit that 1 mole of gas occupies 22.4 liters. And that is always, always, always true. Yes, the universal gas constant, which we'll get into in a little bit. I gotta verify my live again. Love it. Okay. Okay, so we have Boyle's law, Charles' law, and Avogadro's law. Those are the 3 types of laws. But we can go further. and we can combine all of these gas laws into the combined gas law. Now, the combined gas law takes Boyle's law, Charles' law, and even Avogadro's law, and combines them all into one. Most of the time, you will see this as P1 V1 over T1 equals P2 V2 over T2. So that is the main one that you will see. P1 V1 over T1 equals P2 V2 over T2. Occasionally, you might see one where it includes moles as well. Technically, that is also true, but it's not entirely shown that way a lot of the times. So I'm going to ignore that for now. So P1 V1 over T1 equals P2 V2 over T2. This is one of the most important ones that you are going to want to remember. Because if you know your combined gas law, you know Boyle's law. Because at constant temperature, we just end up with P1 V1 equals P2 V2, because our temperature is not changing. Then if we look at Charles' law, it's at constant pressure, well, we look at V1 over T1 equals V2 over T2. There's Charles' law. And then Avogadro's law we don't really care about, to be honest. So if you can remember, or you can figure out this combined gas law, then you're good to go. Now, all of these laws previous, so Boyle's law, Charles' law, Avogadro's law, and even the combined gas law, all of those are when we're going from one situation to another situation, where we're changing something about the system, about the gas, where we're changing the pressure and seeing what happens to the volume, or we're changing the temperature and the pressure and seeing what happens to the volume. But if we're just talking about one particular instance, then we can go and talk about the ideal gas law. And that uses the combined gas law, this I'm going to sort of write it out, PV over, if we use the Avogadro, that mole, NT. Now remember, we had some constant on that mole, so I'm just going to put a constant there. And essentially what we're saying is PV is proportional to 1 over this whole thing, giving us, if we were to rewrite this whole thing, giving us PV equals N times some constant R times temperature. And this is our ideal gas law. This is going to be one of the most important equations that you use when you're talking about gases. So let's talk about what this says. Well, our pressure, or our P, that is for pressure, so the pressure of the gas. V is for volume. N, well, that's number of moles of our gas. Let's talk about T first, that's temperature. And then this R value. This R value is our universal gas constant. It is a constant, it will never change, and that constant is 0.082. Now, in some cases, it might be 0.0821, 0.0820067, I think. But for now, we'll just go with 0.082, and it has very funky units, as liters times atmospheres all over Kelvin times mole, or mole times Kelvin. This ideal gas constant, this R value, tells us exactly what units all of the other values need to be in. When we're working with pressure, we have to be in atmospheres. Volume, we have to be in liters. Moles, well, that's moles. We have to be in moles. And then temperature, we have to be in Kelvin. So we have to be in these units here in order for us to be able to plug into the gas constant. There is another form when we're talking about energy in terms of the R value, but I'm not going to show that here just so we don't get confused. But this gas constant tells us everything else that we need to know. Now, in all of these cases beforehand, the combined gas law, Charles law, and all of those were when we were taking one system and changing something about it and looking to see what happened. In the ideal gas law, we're looking at one particular moment in one particular gas. We're not changing anything. We're just looking at the relationship between the pressure, volume, number of moles, and temperature at a particular time. So that is the ideal gas law. We'll use that in a little bit to sort of solve for some stuff. But there is another variation. And the variation, if we think of this as Puvnert, the other variation is, I'm going to use purple here. The other variation is Pumdirt. So we have PV equals nRT, and we have PM equals DRT, where now pressure is still the same, R is the same, T is the same, but now this M is our molar mass of our gas. We can find that on the periodic table. Yes, this is the density one, and our D here is density of the gas. So if there can be a question where we're either given the density or we're looking for the density, and so we can just solve using Pumdirt versus Puvnert. So you can either use Puvnert, or PV equals nRT, or Pumdirt, PM equals DRT. Ideal gas law, the PV equals nRT, that is given on the helpful information sheet for the AP test. This one is not. So this is one that you will have to kind of remember, and I just say Puvnert and Pumdirt. That's how I was taught, and that's how I remembered. And so this is sort of our relationship here. Then we get into Dalton's law. So Dalton's law stands for, well, Dalton, I like the name Dalton. Dalton found out that when we're talking about partial pressures, if we have more than one gas in a system, let's say we have nitrogen, oxygen, and helium all in one container. Well, if we want to find the total pressure in the system, if we want to find the total pressure, well, we can just add up all of the partial pressures. Partial pressure of 1 plus the partial pressure of 2 plus the partial pressure of 3, and so on and so forth. And so Dalton just said, well, the total pressure of the system equals all of the partial pressures. But what do partial pressures equal? Well, partial pressures, they're going to equal the mole fraction, oh, my voice cracked, the mole fraction of our gas times the total pressure in the system. So if we know the total pressure in the system and we know how many moles we have of a gas, then we can figure out the partial pressure. So this is Dalton's law of partial pressures, tells us the sum of all of them equals the total. And then we could also use the total to solve for a certain partial pressure. Whew, that was a lot. I think that's, yeah, so that's sort of a very brief overview of just all of the different gas laws. How are we doing on all of that? We did some on intermolecular forces today. We did some on gas laws in terms of this. Just going over the brief stuff. We are going to start going into some practice problems, but I just want to check in and see how we're doing. While I wait for some answers, I'm just going to take a sip of my coffee. Very clear and concise teaching. Oh, thank you. I know the AP test is like, 3 weeks away, we found out? Oh yeah, I can definitely explain this last part. So let me get a new page here. So let's say, add page, there we go. So we have this equation. I'm going to use A instead, so we can sort of look at it as a gas. So we have this equation here, where we have the partial pressure of some gas A is going to equal the mole fraction times the total pressure. So this sort of just tells us a percentage of the total. That's really all it is saying, well, if we know the total pressure, a mole fraction is just a percent, right? It's part over whole. So if we look at a mole fraction of A, that's going to be the number of moles of A over the number of moles of A plus whatever is in our system. So moles of B, moles of C, whatever gases we have. It's giving us sort of a part over a whole. And that's what a mole fraction is. It tells us the parts, or the number of moles that we're worried about, over the whole or total number of moles. So if we know the certain percentage of our gas A, and that percentage, if we multiply by our total pressure in the system, well, we're going to figure out that the partial pressure of that equals just the multiplication of those, or the product. You can also think of it as like gases have minimal IMF toward one another, so they have a lot of empty space for other gases. Yes, yeah, exactly. So yeah, this is a good thing. Oh, the other thing that I forgot to mention, the difference between a real gas and an ideal gas. So ideal gases and real gases. That is something true, or there's a difference between these two. An ideal gas, we want the least amount of interactions as possible. And so, yes. So we want the least amount of intermolecular force interactions as possible. Because for a gas to behave ideally, we can't have it interacting with other things. So we want something that's either inert, meaning it doesn't react, very low, I'm going to actually write low LDF, all of those different types of things. Whereas real, it really can be anything. We don't care. Things are real all the time. But what are the conditions for these? And that's the most important thing. Thank you, IMF. Or no, yeah, IMF. It's one of those nights. Low IMF. Low intermolecular forces. Sorry about that. So what are the conditions that this has to be? Well, if we think of soda, and I made a video on this yesterday or the day before. If we think of soda, how do we like our soda? Well, I don't know about you, but I like my soda cold and fizzy. And with cold and fizzy, we have low temp, and right, there's gases in soda. And fizzy, if we have high pressure, we have more fizziness. So we have cold and fizzy. And since soda is real, these are the conditions under which gases behave real, or real gases. The opposite of this is true for ideal. An ideal gas will behave most like an ideal gas when we have a high temp, so when our gas is at a high temperature, and a low pressure. And so with these two things, we can sort of talk about, molecules at a real gas. We have cold, they're sort of moving slowly, but fizzy, we have high pressure. They're like bouncing off one another. Whereas this, yes, they're moving around more, but we're at such a low pressure that it doesn't necessarily matter. So here we're talking high temp, low pressure, giving us an ideal gas versus real gas. We have our soda that is cold and fizzy. Why was the soda a real gas? So soda contains carbon dioxide. So if you open up a thing of soda, it has carbon dioxide, a gas. And soda is real. Like, we can drink soda. We can't drink something ideal, like an ideal gas. But I like to think of it as real, right? We can physically hold a can of soda. So I like to say, well, if we like our soda cold and fizzy, that's cold temperature, high pressure. That allows us to sort of just a little trick to say, okay, well, a real gas, cold temp, high pressure. Whereas an ideal gas is just the opposite, high temp, low pressure. Okay. We are cruising. We're about an hour and a half in, and I have a hard stop tonight. I know. I have a hard stop at 10 Eastern, so we have half an hour left. So I think the best thing to do now is to skip around and do some practice problems to talk about. Let's see. So we force it in the soda with low temp. Then we say gas is like high temp. Yeah, something like that. Something along those lines. But I think the best thing to do right now is go through some practice problems. Again, if you want access to these practice problems, they are on my link tree. If you just click the link in my bio, you can have access to these practice problems. We'll do some on intermolecular forces, and then we'll go right into some gas law problems. So let's go ahead and start on some intermolecular force problems. And we're going to start with, see you later. We're going to start with number 1. Oh my goodness, if I can get it to stop moving around. So number 1, we're given this table. The electron cloud of HF is smaller than that of F2. However, HF has a much higher boiling point than has F2. Which of the following explains how the dispersion force model of intermolecular attraction does not account for the unusually high boiling point of HF? So now we have 2 molecules here. HF has a higher boiling point than our F2. Now, if we look at HF versus F2 and we look at the intermolecular forces between them, well, F2 versus HF. Well, F2, that is a non-polar molecule, non-polar, and so it only has LDF. Whereas HF has LDF, it is a polar molecule, so it also has dipole-dipole forces, and we have a hydrogen bound directly to a fluorine. So we have hydrogen bonding. And what did we say about anytime we increase the amount or the type of intermolecular force? Well, we're increasing the strength between our molecules, that force between our molecules, and that helps increase our boiling point, makes them stronger, exactly. And so here, we're going to look for one that talks about intermolecular forces, because that's the only difference here. Between just having an atom, we have different intermolecular forces. So here, we can't really talk anything about solubility, just about forces here. F2 molecule has a greater mass. Well, even though it has a greater mass, it doesn't matter necessarily in terms of boiling point. Liquid F2 has weak dispersion forces between its molecules, whereas liquid HF has strong ionic interactions between H plus and F minus. Now, this ionic interaction here tells us that HF is really saying HF is an ionic bond, but HF is a covalent bond. So C is incorrect, leaving us with D, but let's make sure it is the correct answer. Liquid F2 has weak dispersion force attractions between its molecules. That is true. Whereas liquid HF has both weak dispersion forces. That is true. Everything has LDF. And hydrogen bonding interactions between its molecules. And it does have hydrogen bonding, which gives us D as our final answer because HF has hydrogen bonding, giving it a larger or higher boiling point because it is stronger. All right, let's go on to number 2. We're going to do a few intermolecular force problems, then we'll go into some gas law problems, including solving a couple gas law problems. Okay. In the diagram below, which of the labeled arrows identifies hydrogen bonding in water? Now remember, hydrogen bonding is a type of intermolecular force. Inter meaning between more than one water molecule. So if we look at our options here, choice A is between a bond within one molecule. So it's not going to be choice A because we're looking for inter, or between more than one. We have another water molecule here, 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 and here. So let's take a look at those. Option B, if we zoom in on B, we do see some type of force between an oxygen and an oxygen, but remember, different forces or opposites attract, right? We want a positive side to be attracted to a negative side of a molecule. Looking at this, oxygen is more electronegative than hydrogen, so it's going to have a partial negative, and I'll just put a negative charge here. And then, which means this negative charge is also going to be on that oxygen, that other oxygen. Because we have two negatives here, there won't be an intermolecular force. We want a positive bound to or attracting a negative force. So even though there is an intermolecular force here, it is not a correct intermolecular force because it is a negative and a negative. We want a negative and a positive. Same thing here. Hydrogen gives us a positive or a partial positive charge based on its electronegativity, and we end up with a positive and positive. Again, that is repulsion, not attraction. So the only option left is D, but let's double check. We have a negative charge on that oxygen, a positive charge on that hydrogen. It is between two different water molecules, so it is intermolecular. And it is a positive and negative. So our correct answer here is choice D. How are we doing? I hope we're doing good. I'm going to go on to, wait, why not C? For this one, because even though C was between two water molecules, we had a positive and a positive on the hydrogens. We had two different positive values. And so we want a positive and a negative attraction. Amazing. Okay. Let's go on to, let's do number 3. Number 3, in which of the following liquids do the intermolecular forces include dipole-dipole forces? So remember, dipole-dipole forces, those are going to be our polar molecules. So anything that's polar. So we want to look for things that are just polar and not non-polar. So it has to be between two water molecules. Yes, going back to the other problem. So here we have F2. Now we just drew it beforehand, but that would become a non-polar molecule because we have an equal distribution of electrons. If we have CH4, we've drawn this one tonight too. CH4, we have an equal pull in all directions, right? We have an equal pull left and right, up and down. We don't have any displacement or any asymmetrical things. So this would also be a non-polar molecule. Similarly with CF4, it's going to look the same exact as our CH, just with fluorines. And that's going to also be non-polar. And so our last option here, we have C with 2 H's and 2 F's. Now we have a polar molecule. We have an unequal distribution. So this is our polar molecule. And we're looking for something with dipole-dipole forces. And dipole-dipole tells us polar. Our first 3 options, A, B, and C, were all non-polar. Our choice D, CH2, F2, is our only polar molecule. Nice job to everyone who got it in the chat. Okay. Whew. That was a tough one. Because F is more electronegative, yes. So if we were to look at the dipole moment or the difference in electronegativity, it would be sort of favoring this side. Our electronegativity, our pull for electron, that dipole moment, will be favoring the fluorines. Do bonds matter, aka double, when determining polarity, or just the molecule's electronegativity? Just the molecule's electronegativity typically matters the most, as well as the geometries. So you're also going to want, if you have like double bonds, multiple double bonds or triple bonds, you're going to want to look at the molecular or electron geometries when you do that. But yes, typically it's just the atoms. Where are these review questions from? I take them from various AP chemistry resources, or I create my own, depending on if I can find questions like this. Okay. Let's go on to number 4. The London dispersion forces are weakest for which of the following gases under the same conditions of temperature and pressure? So now we're looking at London dispersion forces only. And if we take a look at all 5 of these options, they're all nonpolar, which makes sense because we're only looking at London dispersion. But if we all have London dispersion here, or only have London dispersion forces between these 5 molecules, how do we tell what is going to have the weakest? Well, this is where we look at the molar mass, or the molecular weight. Something with a high molar mass or a higher molecular weight is going to have stronger LDFs, or stronger London dispersion forces. So if we were to figure out and compare the difference in molecular weights of all of these molecules, we can solve for the strength of the London dispersion forces. So going through the periodic table and counting everything up, we have H2 is 2 grams per mole, O2 is 32, xenon is 131 grams per mole, F2 is 38, and N2 is 28. So we're looking for the weakest LDF. So we're looking actually for a low molar mass. The smallest lower mass equals the weakest LDFs. And looking at our 5 options, the smallest molar mass is H2 at 2, giving us our weakest London dispersion. Is it because higher molar mass means more electrons, or because of surface area? It has to do a lot with surface area, I would say, because our molar mass doesn't necessarily contribute to the number of electrons, right? I mean, it does and it doesn't. But it's a combination of both, probably. But I would say it's the surface area or size of the molecule. Do I do this every night? I wish I could, but unfortunately I do not. Yes, the lives are posted on YouTube. I have people already asking about number 5. So let's go on to number 5, and then we can talk about more of these if needed. So, which of the following is the strongest type of interaction that occurs between the atoms within the circled areas of the 2 molecules represented below? So we're talking about 2 different molecules. We're talking about intermolecular forces, right? We're talking about intermolecular. So we can get rid of our bond options, our just covalent bonds, because those are intramolecular. But now let's take a look at our intermolecular forces between these 2 molecules. Well, we have a circled option here and here, as we can see. And it's between, it looks like, a hydrogen and a nitrogen, and a hydrogen and an oxygen. So those are the 2 forces being put out. But what are these hydrogens attached to? And that's going to help us determine whether it's hydrogen bonding or London dispersion. Well, this hydrogen is attached to a nitrogen. And because it's attached to a hydrogen in that molecule, that means that we have hydrogen bonding. Anytime we have a hydrogen bound to a nitrogen, oxygen, or fluorine, we have hydrogen bonding. Same thing here, we have a hydrogen bound to a nitrogen. So we have that direct bonding here between a hydrogen and nitrogen, giving us an intermolecular force of hydrogen bonding. Now, it does have London dispersion forces, but the strongest type of interaction would be that hydrogen bond. Nice job, everyone. I saw a lot of C's in the answer. Hydrogen bond is fun. Yes. I heard that for the first time tonight, and I was very, very excited that I heard it. Okay. So let's go through. Everything has London dispersion forces. So even though it's not specifically shown here, we do have London dispersion forces because those are present in every molecule. So if we're talking about CF4, CH2F2, this giant molecule here, everything has LDFs. It's what comes afterwards that makes the difference. Okay, I want... Those are the same. So van der Waal and LDF are the same. Now, I do have a hard stop in 15 minutes for tonight, so I do want to get to some gas law problems tonight, just so we can have some. And then maybe what I'll do tomorrow is I'll continue going through this. Yes, Gibbs free energy, that is unit, I think that's unit 9, which I think will be next week at some point. A lot of the math equations for gas laws, I can definitely go over some math equations for gas laws. But let me find a couple. I'm going to quickly look through. Let's do... Let's do number 20 to start out. Yes, I'm going unit by unit. Or at least trying to, at least. How often do I go live? I try to go live 3 times a week. With my schedule, it's hard for me to try to do that, especially this upcoming week. My unit list with dates was a pinned post, but then I wanted to pin something else. If you just go on my profile and click like the live button, like upcoming lives, it'll have a list of the current ones that I have scheduled. Yes, the units are different everywhere, but I do put the actual units in the description. So yes. Okay, so let's go through number 20. Which of the following behaves most like an ideal gas at conditions indicated? Well, what we were talking about earlier about ideal gas versus real gas, this we're looking for an ideal gas. A real gas, we like our soda cold and fizzy, so a real gas would consist of a low temp and a high pressure. An ideal gas is the opposite. We want something at a high temp and a low pressure. So if we look here at our answers, well, we are at 20, 20, 20, 20, and the only difference in pressure is H2. And for the most part, we were all at the same temperature. So we want something with a high temp and a low pressure. The only low pressure by a significant amount is going to be H2. That's going to be our answer, even though the temperature is different. It's lower here than our 300. Our pressure is significantly different. It's like 10,000 different from the others. So our answer here is A. We want something with a high temp, low pressure. The only one with a low pressure is option A. Can you do the topics you set up earlier? What do you mean? Like gas laws? I'm ignoring you. Oh no, I'm so sorry. I'm not ignoring you. There's just a lot of things coming in and I'm not really looking at this screen. MCAT level difficulty. Yes and no. They're more specific on they're more specific to AP Chem and Gen Chem, but yes. The schedule, like the one is April 20th and next one is April 27th. Eek. I'm so confused. Hang on a sec. Oh, yes. So the reason why there's a big gap there is because I am out of town presenting at a conference. So I can try, but I don't know how my schedule is going to be, and that's why there is that big gap there because I am out of town. High temp and low pressure is the definition of an ideal gas, or the conditions at which an ideal gas behaves most like an ideal gas. Absolutely. Okay, let's go through. I want to go through some calculations actually, because I think those tend to trip some people up. So what I'm going to do is we're going to go through. Let's go through this one. Like 19? Oh, wait. I'll go back to 19. We'll read this graph. So, I'm going to erase this just for a moment. The distribution of speeds of H2 molecules at 273 Kelvin and 1 atmosphere is shown in the diagram above. Which of the following best shows the speed distribution of helium atoms under the same conditions of temperature and pressure? So when we're looking at this type of graph, what we're really looking at is, and I'm going to zoom in just so I can sort of show you, we have fraction of particles, or essentially number of particles, number of molecules, and speed. So let's think of this as like kinetic energy, right? Or actually, no, let's not think about it as kinetic energy. Let's just think about it as speed. So when we have lower speeds, our fraction of particles are going to sort of be like so. So we have lower speeds, our peak is going to start to increase, our height of our peak. And we sort of just shrink everything up into a nice peak. Whereas if we have longer speeds or higher speeds, more molecules can go through and have different speeds. And so we see this sort of distribution here. Now, in terms of comparing things, we can look back at molar masses and stuff. So let's take a look at a couple things. When we're looking at size of the peak, so a bigger peak, that's going to be characteristic of a larger molar mass. So the heavier we are, the larger the molar mass, the bigger the peak. But then also, the slower the speed, the heavier we are. Similar sort of thing. Bigger peak, heavier, that sort of thing. So if we're looking between H2 and helium, well, helium is larger than, helium is heavier than hydrogen. Hydrogen weighs 2, helium weighs 4. So because we have a larger molar mass for helium, it's going to have a bigger peak. And when we're heavier, our molecules can't move as fast. That's what it is, sorry. So when something's heavy, if we think of like dumping a box of ping pong balls downstairs versus a box of basketballs. The basketballs are going to go everywhere, but they'll sort of be a little more contained. They won't travel as fast. But ping pong balls, they'll go everywhere all the time. It's more chaotic. And so the heavier something is, the slower it's going to go. So because we're talking about hydrogen and helium, we have helium, which has a larger molar mass, And a larger molar mass means slower speed. So we can sort of draw helium in like this. It's a bigger peak and it's a slower speed. And that's what this means here. And so if we're looking at comparing hydrogen and helium, well, the only one that sort of represents this curve is choice A. Why are you making so much sense? I try to make as much sense as possible. A lot of these concepts are challenging, and it took me a long time to be able to understand them. So, yeah, let's, if we had something even heavier, like argon, for instance, argon is much heavier than helium. So let's say we had argon. So this is hydrogen, this is helium. Argon is much heavier, so we're going to have a bigger peak, and it's still going to be slower. And that's sort of the trend that we want. This becomes argon, and so on and so forth. And the lighter we get, the sort of more smoothed out and further they can go. Perfect. You're going to binge watch your other sessions on YouTube? Thank you. Some of the sessions they're long. They are long sessions. So by the end of it, I was getting a little tired. Okay, I have about six minutes left. So what I'm going to do, I'm going to go through a couple, some calculation problems. So let's go through, I'm going to go all the way over. And we're going to go to these gas law problems. So we'll do two of these problems. We'll do number 1, and then we'll do number 5. Yeah, number 1 and number 5. Okay. So number 1, a balloon is filled with 3 liters of helium at a pressure of 1 atmosphere. What is the volume of the balloon at an altitude where the pressure is 0.7? So here, when we're setting up a problem like this, what I like to do is sort of make a knowns list. And every time I come across a known, I just write it off to the side. So we have a volume equaling 3 liters and a pressure of 1 atmosphere. What is the volume? So now we're looking for a new volume when the pressure is 0.7. So we have a new pressure. Now, because we have multiple V's and P's here, we are going to want to denote that as V1, P1 and V2, P2. Now, what type of law is this going to be? Well, this is our Boyle's law, right? P1, V1, we're only working with pressure and volume, equals P2, V2. I like bottles. I know you meant Boyle's, but I love that it auto-corrected to bottles. So now we can go ahead and plug our values in. You could also just rearrange, if we're solving for V2, if you wanted to, you could rearrange this. That way you don't have to do a lot of the math. You can do V2 equals P1, V1 over P2. This is sort of like Gen Chem 2, but you might have to do it for AP in terms of these types of calculations. So let's go ahead and plug this in. V2 equals, we have, 1 atmosphere. So we have 1 atmosphere times 3 liters all over 0.70 atmosphere. And that gives us a volume, if we were to solve it out, of 4.3 liters. Now, it's always a good idea when you do these calculations to go back and check to see, does that make sense? We know that there is an inverse relationship between pressure and volume. So as our pressure increases or decreases, the volume will do the opposite. So what happened here? Well, our pressure decreased. We went from 1 atmosphere to 0.7 atmospheres, which means our volume should have increased. So let's double check just to make sure that did. We started out with 3 liters, and we ended up our calculation with 4.3 liters. So that is exactly what happened. So we know that we at least went in the right direction. And so, yeah, this would be our final answer. As our pressure decreased, our volume increased. All right, let's go and do... We're going to do... How many sig figs? Absolutely. So because we're working with, oh my goodness, so many things. Because we're working with multiplication and division, the rule for multiplication and division is least number of significant figures. Now, I didn't show it here in my work, but we always go back to what's given. So this 1 atmosphere came from here, so that was 2 significant figures. The 3 liters was here, and that was 3 significant figures. There's a decimal, which means there are 3 significant figures. Those zeros count after the decimal. And then we have that 0.70, so that value here. The leading 0 does not count as a significant figure, so we have 2 sig figs here. So when we do significant figures for multiplication and division, we're looking for the least number of significant figures. And between 3, 2, and 2, we end up getting needing 2 significant figures in our answer. I believe this answer would have been like 4.29 something when I did it earlier, which is why it rounded up to 4.3, because we only wanted 2 significant figures in our answer. All right, so let's go on and do number 5. I do not teach organic chemistry. I'm focusing right now mostly on Gen Chem, AP Chem, Honors Chem, those types of courses. But let's go on to number 5. It's a little hard to see, I'm sorry. But this will be the last question tonight, just because I do have a hard stop in a couple minutes. But let's go ahead and do number 5. A mixture of 6 grams of oxygen and 9 grams of CH4 is placed in a 15-liter vessel at 0 degrees Celsius. So there's a lot of information here. What is the partial pressure of each gas, and what is the total pressure in the vessel? So we have a couple things to solve for in this question. We're looking for the partial pressure of each gas, so we're looking for 2 partial pressures, and we're looking for the total pressure in the vessel. So let's go ahead and figure out what we are given. So we're given, oh gosh, let's see what we're given. Well, we're given a molar mass of oxygen. Oh, well, I'm going to write it out like this. We're given 2 gases. So I'm going to write oxygen and I'm going to write CH4. And we're going to sort of just split right down the middle and figure out what we're given. Well, we're given a mass of O2, which equals 6.00 grams. And we're given a mass of CH4 of 9.00 grams. In both of these cases, our volume is going to be 15 liters. And our temperature is 0 degrees Celsius. Why do I want to write degrees first? That's a funny one. I've never done that before. So those are what we have so far. What is the partial pressure? So we are looking for the partial pressure in each case of each gas, and what is the total pressure? So we have quite a few things here. We have pressure, temperature, volume, and a mass, which from our mass, and we're given a molar mass, we actually can find number of moles. So if we can find the number of moles in our gas samples, well, we can use our PV equals nRT, our ideal gas law. And we can solve for pressure in each of these cases to solve for the partial pressure of each of our gases. So we have to do a couple things first, though. First thing we want to do is convert our mass of each into moles because we can't plug in mass. We can't plug in grams into our ideal gas equation. Our N has to be in moles. So to do that, we're going to divide both of our masses by the respective molar masses. So we end up with, I'm going to do this. We have 1 mole on top and 32.0 grams on the bottom, right? What goes up must come down. Someone commented that today in terms of units. So if something's on top, it must come down. And that will give us some value. And I'm running out of room. Here's what we're going to do. We're going to do this and just move this over. So this gives us a moles equaling 0.1875. And then we'll do the same thing for our CH4. CH4 is 1 mole over 16 grams, giving us a total of 0.5625 moles of our CH4. Yes, it is notability. So let's go through. Now that we have our pressure, or we're looking for our pressure, we have a volume, we have number of moles. R is our ideal gas constant. That is a constant. It will not change. And temperature we have, but remember, temperature cannot be in Celsius. It has to be in Kelvin. Whenever we're doing any sort of gas equation, gas law equation, we have to be in Kelvin. So this becomes 273 Kelvin, and that'll be the same for our CH4. Now we can go ahead and plug into our ideal gas law equation to find our partial pressure. And before I do that, though, I'm just going to rearrange this partial pressure of our oxygen. If we divide both sides by volume, we've solved now for partial pressure. So now we can just go ahead and plug in our values without having to rearrange things later. So we plug our values in. Our partial pressure is going to equal the number of moles, which is 0.1875 times R, that is the ideal gas constant that is given to you on the sheet, the helpful information sheet, times our temperature of 273 Kelvin, all divided by our volume of 15 liters. It gives us a partial pressure of oxygen after it's all said and done, equaling 0.280 atmospheres. Now that is the partial pressure of oxygen. That is one of the 3 things that we were asked to solve in this question. The other question one of the other things that we had to solve was for the partial pressure of CH4. So let's go ahead. We're going to plug in. So using the same equation, we have partial pressure of CH4, the ideal gas law. We're dividing by our volume, nRT over V. We can go ahead and plug everything in. We have partial pressure of CH4 equaling 0.5625 moles. I'm going to run right out of room. 0.082 and 273. There we go. Fit it all in. And then we'll divide all of that again by our 15 liters. When we solve for the partial pressure, we end up getting a value of 0.839 atmospheres. And that's just plugging into the calculator and solving. Now again, that is number 2 of the things that we needed to solve for, right? We just solved for the partial pressures of each of our gases. Our partial pressure of oxygen was 0.280, and our partial pressure of methane, or CH4, is 0.839. What else do we have to solve for? Well, what is the total pressure in the vessel? How do we solve for total pressure? Well, total pressure, according to Dalton's law of partial pressures, is going to equal the partial pressure of our oxygen plus the partial pressure of our methane. Dalton's law, yes, exactly. So Dalton's law of partial pressures, adding both. So if we want to find our partial pressure, we're just going to take our 0.280 atmosphere, or total pressure, sorry, plus the 0.839 atmospheres, and that'll give us a total pressure in the system of 1.12 atmospheres. And that is our final answer. Whew. Dalton's law isn't terrible. Dalton's law is just this here. We have total pressure equaling the sum of all of our partial pressures. That's all Dalton's law is. So it's like saying you have coins and you want it to add up to 100. So you have like 5 pennies, 9 dimes, and a nickel. Add them all up, it equals the total. In what situation is Dalton's law used? Anytime we have a mixture of gases in a container and we want to solve for either the total pressure or a partial pressure of one of those gases, because each gas will have a different partial pressure, it'll have its own respective pressure. I've always done total pressure with another PV equals nRT. Looks like there was an easier method. Yes, definitely is an easier method to do. We love Dalton for that. I also saw a question that was like total pressure then multiplied by mole fraction. That was the other thing. When we're using, like, let's say we didn't know partial pressure of oxygen, but we knew the total pressure, you would use the mole fraction of oxygen. That's a terrible mole fraction. Mole fraction of oxygen times the partial pressure. So it's like giving you a percentage times the total pressure. And that is the other type of equation that is used. There are a couple problems in here using that equation, and I will post the answer key as soon as this live is done. But yeah, so now what I'm going to do is I'm going to helping you hopefully with this. I do have a hard stop, so I am going to have to get off a little bit earlier tonight than normal. I will be live again tomorrow night, going over probably more of these types of problems and getting into solutions chemistry. So talking about molarity and molality, and starting to look at concentrations and those types of things. The dilution equation and all of that. I will be posting this on YouTube as soon as it's available. And then I'm a mess right now, but if you want these packets of practice problems, then you can go to just click on the link in my bio and then click the like helpful information one. And it will bring you to Google Drive with all of the resources that I have on there, as well as these questions and answer keys. Channel name the same? Yes, I think it is, just without the period in between, or you can just go to my profile and click on the YouTube link. All of these videos go on YouTube as soon as they're available from me through TikTok. And I hope everyone has a fabulous, it's Monday night. I almost said Tuesday. Have a fabulous Monday night. But before you go, remember, keep on being amazing. I know the AP exam is in 3 weeks. You got plenty of time. Start a diagnostic test. See where you're struggling, and dream of chemistry. I love that comment. Keep on being amazing. You got this. I know you do. I believe in you. All right. Have a good night, everyone. I will see you all soon.